we were talking about subgame perfect Nash solution. One of the questions that your friend asked when we started studying them was, what if, so what we had was, if the game is a finite perfect information game, then we're guaranteed the existence of at least one subgame perfect Nash solution, which we can find using the backward induction algorithm. So one of the questions that one of your friends asked was, what if the game is not a perfect information game? So let me just give a fast, simple example on how to deal with it, with such cases. So player one starts as two strategy actions, A, B, and after that player two takes an action, can choose left, right. If player one chose A, then it's player two's turn to take an action. He or she can take small l, small r. If player one took the action B, again, it's player two's turn to take an action. He or she can take the actions capital L, capital R. But agent one is not able to observe the action of player two in that case. And he has to take an action. He can take the action capital A, capital B. Because they're in the same information set, the set of actions available at any node in this information set, we know that should be the same. So let me put the payoffs, numeric representation of the preferences. So the numbers. Okay. So that's our game. So this is not a perfect information game because at least one player has an information set which contains more than one history, more than one node. Okay. So how do we deal with it? Yes, sir. Okay. So first of all, how many subgames do we have? In this game, we have only three, right? One of them is this, the subgame following this node or history. The other one is this, following the part of the game following the action B, that is following this node. And the third one is the game itself, right? Okay. So, for example, this is not a subgame of this game. We cannot cut this part out, okay? So the green part is not a subgame. So we have three subgames, and your friend chose one of them. You chose the one on the right. So your friend decided, again, what he's doing is using the idea of the backward induction algorithm. So he starts with a small game, okay, which could be the game on the right, the game on the left. He decided to start with this. So we concentrate just on this game. So actually, let me erase the green. Okay. Yeah. So any subgame perfect Nash solution of this game, when restricted to this subgame, should be a Nash solution of this subgame. So your friend started with this. So how do you find the Nash solutions of this game? If in this subgame, each player has two strategies, so we can use a matrix representation maybe. So again, we'll use rows for player one, A, B, L, R, and the payoffs are when player two plays L and when player one plays A, that's 4-3. And when player one plays B, player two plays L, the payoff is 1-0. And then going similarly 2-1, 2, 4. Okay? So we're looking for the Nash solutions of this game. By the way, for now, we're just restricting attention to pure strategies. So I can easily look at the best responses. So we have 2 Nash solutions of this subgame, okay? Which actually, let me mark them on here. Player 1 plays the strategy A in this game, okay? Which means that takes the action A in this information set, okay? And player 2 takes the action L at this information set. So I'll represent those with arrows, okay? That's one Nash solution of this subgame. And the other one was this, okay? So player 2 takes the action R at this information set. I'll use the red for that. Or, if the exam, you can use double arrows to discriminate between the two. Okay? And player 1 plays B. Okay? Which I should mark both. Okay? Okay? So far, so good? So then what we do is, again, just like we did with perfect information, finite perfect information games, we remove this subgame and replace the starting node of that subgame with the payoff resulting with the Nash solution of this subgame. Well, there are 2 cases, so it means that I have to do 2 separate cases, okay? So what I'll do is actually, let me draw 2 pictures, because that's roughly how I would like to see it on the exam. Well, actually, let's also analyze this game, this subgame. Okay. So that's a 1-person subgame. Nash solution is just a maximizer of profits. So here, L is a Nash solution of this subgame. 1 person, just maximizer. 2 is better than 1. 2 is greater than 1, so L is preferred to R. Okay? So then I can actually reduce this game to the following game. 3, 2, 4, 3. Okay? In that case, what will player 1 do? Again, that turns out to be a 1-person game. Maximize, choose the action which maximizes profit with payoff, which is to choose B. So, okay. Or we could have replaced this subgame with the payoff 2, 4. In that case, we have 2, 4. This time, B is the maximizing choice. Okay. Okay. And actually, we're done. So let me mark that here too. Okay. Any questions? So, subgame perfect Nash solutions. If I follow the arrows, subgame perfect Nash solutions will come out. Okay. Will come out as Nash solutions of the game gamma will be A, L, okay, and then B, B, give me a minute, A, L. Okay, so far so good? Okay, some of you are not happy. Anybody else who are not happy with this? More? Okay, what's the problem? They are the actions that are taken under the subgame perfect Nash solutions. Here, when you're writing subgame perfect Nash solutions, again, a solution is always a strategy profile, okay? So this is not a strategy of player 1. This is not a strategy of player 2, okay? So that's why, in general, it's a good habit to, before you start solving the problem, it's a good habit to, if possible, write explicitly what the strategy set of the players are. Sometimes it becomes too complicated, but even in that case, it's a good idea to think about what kind of an animal is, so that at the end you can check your work. This cannot be the case, this cannot be the case, okay? So they have to be strategy profiles. So what are the strategy profiles? It consists of a strategy of player 1. Let's first use the black one. The black one says, take the action B for player 1, take the action B at this information set, and take the action capital A at this information set. So B, what did I say, capital A. And for player 2, take the action small l at this information set, take the action capital L at this information set. Okay. So this is a subgame perfect Nash solution, and the action induced by this subgame perfect Nash solution is player 1 takes the action B, let me write it like that. Player 1 takes the action B, and player at the first information set. Then player 2 takes the action L at this information set, and then player 1 takes the action A after player 2. Okay, so the action sequence or the history induced is B, L, A. That's the history induced as a result of this subgame perfect Nash solution. This pair is not a subgame perfect Nash solution. This list is not a subgame perfect Nash solution. That's the history induced by this profile. That's the actions that agents take under this subgame perfect Nash solution. And the other one is the red one. At this information set, player 1 takes the action A. Now I'm following the red. And then here at this information set, player 1 takes the action capital B. And player 2 at the first information set takes the action small l. At the second one, he takes the action capital R. Actions induced. Player 1 takes the action A and then doesn't take an action again. Player 2 takes the action small l and then doesn't take an action again. The history induced is the terminal history AL. Okay? So far, so good? So far, so good? Any questions? Again, don't make this mistake. This is not a subgame perfect Nash solution. It's not a strategy profile. This pair is not. This is. Okay? Any questions? So it's still the basic, the backward induction algorithm still works here. Of course, the problem here, you see, we have a game here. What we did was wrote the strategic form equivalent of that game and found the Nash solutions. Well, here we were lucky that strategic form game had a Nash solution. It could be the case that it doesn't have a Nash solution. In that case, I would conclude that this game has no subgame perfect Nash solution. Okay? So far, so good? Any questions? Any questions? Yes, sir.
Why is 3-2 a Nash solution instead of 4?
What is 3?
3-2.
Where did 3-2 come from? First of all, 3-2 is not a Nash solution. It's a payoff assigned to an outcome, to a terminal history. Okay? So that's another mistake which is very frequently made. Okay? They shouldn't say that 3-2 is a subgame perfect Nash solution or a Nash solution, or 4-3 is a subgame perfect Nash solution. Okay? Those are payoffs, numeric representations of preferences, numbers corresponding to numeric representations of the preference. So your question is, why is, so that payoff, so let me write, these are these theories. Let me also write the payoffs associated with those. 4, 3, 3, 2. So why is this payoff? Why is this strategy profile a subgame perfect Nash solution? Okay. Well, because it's a strategy profile which, at each subgame, the restriction of that strategy profile to each subgame is a Nash solution. So for you, it doesn't look reasonable, I guess. Why?
For example, for the first subgame, why didn't we choose the strategy R, for example?
For here? Well, if you are player 2 and you know that player 1, so I'm player 1, I played A, what would you do? You'll play L. Why? L yields a higher payoff. L, the outcome induced by playing L, is preferred to the outcome induced by playing R. Yeah, okay. Okay. Of course, I guess the problem that you're probably having is this, the outcome induced by, well, this strategy profile is actually Pareto dominated by this. Okay. So maybe we could look at an even further refinement of subgame perfectness, which eliminates cases like that. Okay. Let me give you an even more extreme example. Let me change the payoffs here. I'll just change it simply. Okay. So. What is the subgame perfect Nash solutions of this game? What is the set of subgame perfect Nash solutions of this game? There is none, right? This modified game does not have any subgame perfect Nash solutions. Why? Because this subgame does not have any Nash solutions. Okay? Even though it looks very reasonable that player 1 would play A and player 2 would play L. Okay? But if you're using the subgame perfect Nash solution concept, it yields nothing. Okay? So far, so good? So far, so good? Any questions? Any questions? So, let's look at other examples. So we looked at the case where, our starting point was every finite perfect information game has a subgame perfect Nash solution. So we looked at the case where the game was not finite, but it was of finite length, finite horizon. So we looked at, for example, the Steckelberg model of a duopoly. That was not a finite game, okay, because there was infinitely many nodes, but it was a finite horizon game. After 2 actions, the game ended, okay? So this is a game where the number of nodes is finite, but it's not perfect, okay? So let's look at a game which is of infinite horizon, okay? So Well, I have two choices. I keep going between them on which one to start with, but let me start with this one. A very simple game. So player one starts. He has two choices. He could decide to stop the game or continue with the game. Okay. If he stops the game, his payoff is 1 and the payoff of the second player, while the numeric representation assigns the numbers 1, 2 to this terminal history. If he chooses C, then it's player 2's turn to take an action. He can choose S, stop, or continue. If he chooses stop, then I'll just say payoffs, but by payoff what I mean is the numbers assigned by a numeric representation is delta times 2 for player 1, delta times 1 for player 2, where delta is a number between 0 and 1. Okay. So if player 1, 2 chooses continue, then it's player 2's turn to take an action. He can say stop, continue. If he chooses stop, his payoff is delta squared times 1. The payoff for player 2 is delta squared times 2. And then if he says continue, it's player 2's turn to take an action. He can say stop, continue. If he says stop, the payoff for player 1 is delta cubed times 2. The payoff of player 2 is delta cubed times 1. And the game continues on this like this. Okay. So it's possible that this game never ends. Okay. So there's a history of length, of infinite length. So, question, find the subgame perfect Nash solutions of this game. Actually, even before that, as I said, before you start solving these problems, it's always a good idea to think about what the strategy sets of the players look like. What is the strategy set of player 1? Think about it. It's always a good idea to think about these before you start solving the problem. Come on. What is the strategy set of player 1? Write it down, and if you like me to write it down, I'll take a look at it. Those who have written, if they can raise their hand. And if anybody needs a paper, scrap paper, I can provide some. Anybody need paper? Want paper? Uh-huh. S or C, exactly, right? So when you talk about a strategy of player 1, you have to say what action the player will take at each information set, irrespective of whether the information set is reached or not. Okay? So, for example, at this information set, well, by the way, this is a perfect information game, right? Every information set consists of a single history, so I can say this information set or this history, they are equivalent. Player 1 can take the action S, and then at this information set, even though he takes the action S at this information set, he will not come here. A strategy should still specify what he would do at this information set. So he could choose the action C. At this one, he could again choose the action C. At this one, he could choose S, and then S again, and then C again. And then how many information sets does a player have? Infinitely many. So it will be a infinite sequence of S's and C's, okay? So how can I write them? There are several ways. I can think of that as a sequence of actions. So I will say a t from 1 to infinity, where for any t natural number, at is an element of C or S. That's it. Okay, that's it. Okay. Again, of course, you should write what the interpretation of this is, where a strategy, I'm not going to write it, but you should make a habit of explaining to your reader what this means. A strategy of this type means that the first player, actually this is true for both players, the ith player will take the action AT when it is his turn to take an action the t time, okay? Okay. The t time that he is asked what action he will take the action AT. That's how we interpret this, okay? So far, so good? Well, one of your friends had a different interpretation. He just said, let SI be subsets of natural numbers. And his interpretation was, I will just specify when he will, was it continue? Or he chooses one of them and says, I will just, so if, for example, if we take the set 1, 3, 4, so at the first history, I will continue. At the second, because it's not in the list, I would choose stop. At the third, I will choose continue. At the fourth, I will choose continue. And at all other histories, I will choose, or nodes, I will choose stop, okay? This is also a representation of a strategy for this game, but this is easier to interpret than this one. But they're both, so there's more than one way to write the strategy, okay? You should choose the one that is convenient for you. But the key thing here is player 1 and player 2 have infinitely many information sets. And whether they arrive to that information set or not, a strategy should specify what action the player will take. Okay? So far? So good? Okay.
I want to say that
What can converge to 0? The Prof. So as we go on, well, because delta is less than 1, the payoffs will converge to 0, yes. So what do you mean by the right wing? You mean the very end node? So change this to this action to 0. So based on what? Well, you see, the game is fixed. It doesn't converge anything anywhere. But as the length of the terminal histories increases, so this is a terminal history of length 1. This is a terminal history of length 2, a terminal history of length 3, terminal history of length 4. As the length of the history increases, the payoff assigned to that history converges to 0. I can't say the game converges. The game is a fixed game. It doesn't go anywhere. Okay? But the histories get longer and longer and longer. And as the length of the history increases, the payoff assigned to it approaches to 0. But that's no reason why I should replace this with 0. But yes, that's what what we'll try to do is find subgame perfect Nash solutions of this game. Okay? First of all, do we know the existence of subgame perfect Nash solutions of this game? Yes? Based on what? They will always choose stopper. We'll have a maximizer. Well, so at each node, you're saying that there's only a single number, 2 actions, and they choose between them. Hence, there's a maximizer. Well, we have to be careful. First of all, the theorem which we had, okay, which relied on this backward induction, does not work here, right? Because it's not a finite game. You cannot use backward induction. You cannot start from the very end of the game because there is no end. You cannot start from the very end of the game and move upward. Well, if I can't do that, I don't know what to assign to this node. So that I can say, well, at this node, at this history, player 2, if he chooses S, his payoff is going to be this. And if he chooses C, his payoff is going to be this. Well, I might be able to assign something here, but I can't do it using backward induction. So we have to be more creative. Okay? You all see that? There's no end. And hence, we cannot use backward induction. So, what to do? Well, before what to do, another mistake that people sometimes make is they analyze this game and then they say, well, let delta go to 0. And then they will say that, well, if delta goes to 0, then the Nash solution converges to, the subgame perfect Nash solution converges to this. And let delta go to 1, and when delta goes to 1, the subgame perfect Nash solution converges to this, and hence the subgame perfect Nash solution when delta is equal to 1 is the limit of the subgame perfect Nash solutions that we find for intermediate delta. Okay? Now, what is the problem when delta is equal to 1? Sorry? Sorry? It never stops.
Delta goes to 1, then everyone will say choose stop, sorry.
Everyone choose stop. Sorry? Identical subgame. What else? Anybody else?
I was going to say the game repeats itself, so that subgame becomes the game.
The game itself. Exactly. Very good observation. But there is a serious problem. Okay? So you see, when you're specifying a game, we said, you have the player set, you have the histories, and then you have preferences over histories, which we took care by assigning payoffs to histories, terminal histories. Okay? So, terminal history, S, no, I'm sorry, not SS. C, infinite C's. What is the payoff assigned to this when delta is equal to 1? Sorry? It's impossible to, well, with this specification, you can't see what it is. So when delta is equal to 1, this game is not well defined. Okay? So it's not meaningful to talk about the subgame perfect Nash solution of this game when delta is equal to 1. Okay? Every history should be assigned a payoff. Agents have preferences over histories. So I should be able to compare this history with other histories or assign a payoff to it. Okay? Well, without explicitly saying, when delta is less than 1, the payoff we assigned to this history was, for both players, 0, right? We didn't explicitly say it, but it was kind of obvious from the picture. But I should maybe have specified that the infinite history is assigned the payoff 0. It's the worst outcome for both players. I should have said that, okay? When delta is equal to 1, the game is not well defined. And hence, it's not meaningful to talk about subgame perfect Nash or whatever of this game, okay? If you want to do that when delta is equal to 1, you should assign a payoff to this too. You should specify what happens in this case, okay? So, but the nice thing that came out, which I didn't expect, was when you said when delta is equal to 1, subgame of the game was identical to the game itself. Okay? That's something, you know, we lose something by an infinite horizon game. We can't use backward induction. But we gain something actually with an infinite horizon, okay? Which when delta is equal to 1, okay, this game and this game, as you have noticed, are identical. So the subgame perfect Nash solution of this game is also a subgame perfect Nash solution of this game. Actually, we can even say more than that. Consider this game. So if S1, S2, this profile, S1 is a strategy of player 1, S2 is a strategy of player 2. In this game, actually, let me give a name to this game. Let me call it Gamma 1, the game where player 1 starts. And let me give a name to this game, Gamma 2, the game in which player 2 starts. So if S1, S2 is a subgame perfect Nash solution of the game Gamma 1, then S2, S1 is a subgame perfect Nash solution of the game Gamma 2. If and only if, right? What is the relation between this game and this game? Make all the 1s a 2, all the 2s a 1, and switch the payoffs. Just renaming agents, nothing else, right? Right? So far, so good? Sorry? Yeah, we just swap them, okay? But essentially, if you say that this is the payoff of player 1, this is the payoff of player 2, when you rename this as player 1, that becomes the payoff of player 1. Okay? I'm sorry. You see, the way we wrote it, I should have said, this is U1 of is 2 delta, U2 of is equal to 1 delta. So when you make this 2 into a 1, you make this 2 into a 1, and this 1 into a 2. Okay? So far, so good? So that symmetry between the original game and its subgames is actually a powerful tool, which will enable us to find subgame perfect Nash solutions of this game if they exist. Okay? So think about it over the break, as if you don't have anything better to do. After the break, we'll analyze this game, and then some